sum is always greater than or equal to 0, and greater than or equal to 1 if n is a square. So it's trivial, but it's useful. So first, so the proof, need only establish this for prime powers, and you have done this before with your tau and so on, because I've only got 0 and 1, so if it is greater than or equal to 0 for all prime powers, it's greater than or equal to 0 for all n. If it is greater than or equal to 0 for even powers, it's greater than or equal to 1 for all squares. Okay, so we need check only for prime powers. So if n is a prime power, the value chi of p is either 0, 1, or minus 1. So this sum starts off with 1, but then after that, it could either be all zeros or it could have, if it's all plus 1s, you get positive. If it is minus 1, then the next one will be minus 1 squared, and therefore there is no way that the negatives will outweigh the positives, so this is always greater than or equal to 0. Now when will this be 1? Greater than or equal to 1? Precisely when you're when you have a square, because then this is an even power, right? So you always end up with 1. Then you'll say, so why not we say equal to 1? Well, this could be the principal character, in which case this could be alpha, which would be greater than 1. So this is true. Okay? So this is greater than or equal to 1 if alpha is even. That's it. So now let us prove the following theorem. Okay? Here are 8. So right now I'm just taking a bunch of theorems, but I'm going to conclude by stating as a consequence a certain result, and that result will tell you how we're going to finally put everything together to get Dirichlet's theorem. But to prove that result, we'll take one more lecture. So those of you whom I will have the pleasure of seeing in the new year will see the conclusion of the proof. Otherwise, you just sort of take it with you and imagine how the proof will be completed. Okay, so theorem 8. All right, so so this is the theorem. Let b of x be, let chi be a real character. And b of x be equal to summation a of this a, f of n. F of n divided by square root. Then 1. b of x tends to infinity as x tends to infinity. So this is divergent. And 2. b of x is asymptotic to x times L1 chi. So it's actually of size square root of x. So the conclusion is, therefore, L1 chi, so maybe I should highlight this. L1 chi, real, non-principal, and L1 chi. Somebody has already done this. All right. So I want you to understand the importance of this. We're going to do this in 2 steps. We first show that b of x tends to infinity. In the next step, we actually evaluate b of x accurately. And when we evaluate b of x accurately, we'll end up with 2 square root of x times L1 chi. L1 chi is this series, which we know is convertible. But because b of x tends to infinity, and L1 chi is asymptotic to 2 square root of x, this L1 cannot be 0. So in fact, it proves that b of x tends to infinity like constant times square root of x. Okay, whatever the constant. Now, You see, this is why I made this comment. This series is convergent. This infinite product is convergent. But if you insist on the infinite product being a convergent infinite product at s equal to 1, then by the definition of a convergent infinite product, it can only converge to a non-zero value. And therefore, if you assume or insist or prove that this behavior is in the boundary, then you would have concluded that this L1 chi is non-zero. When chi is non-principal. When chi is principal, L1 chi is 0 or infinity. So mu of n chi of n will become 0. That is the analogous one to mu of n divided by n being 0. Okay, so this is analogous to it. All right, so proof. All right, so first, note that f of n is greater than or equal to 0 for all n, and f of n is greater than or equal to 1 if n is m squared. Thus, your p of x is at least as big as summation 1 over m, but I'm now putting n as an m squared. Right? And this m now is less than or equal to the square root of x. So this is tending to infinity of x. This is the harmonic series convergence. Proving part 1. Now, part of part 2. That's a little bit more involved. That involves the hyperbola method. All right. Observe that. E of x is summation n less than or equal to square root of x, 1 over square root of n. Now this sum is summation chi of b, d divides n, which I can now write as summation n less than or equal to x, summation. I can think of this as a chi of b divided by square root of d times 1 over square root of n over d. So that's your hyperbola. This is a function of d. This is a function of n over d. Which is equal to, let me write this without a mistake. So this is the sum chi of d divided by square root of d, d less than or equal to square root of x, multiplied by this sum, which I would say is q, but that q is now less than or equal to x over d, the hyperbola method, plus, I now sum that part, so the summation 1 over q, q less than or equal to square root of x, times summation chi of d over square root of d, d less than or equal to x over q. And when I do that, as you all know by the hyperbola method, there is a central square which has to be removed, right? Because in the hyperbola method, as you know, we're doing this sum, we're doing that sum, and then we're subtracting. That could be a rectangle. I'm using square root of x. So what I'm subtracting is summation chi of d divided by square root of d, d less than or equal to square root of x, multiplied by summation 1 over q, q less than or equal to square root of x. I've not given any equation numbers today, have I? Okay, so that's equation 1. Okay, so now what can we say about 1? The first term in 1 is summation chi of d divided by square root of d. And now I use the fact that the when I sum the reciprocals of the square root of a number, it's like integration. dt over square root of t is 2 times square root of t. So this is going to be 2 times the square root of x over q. X over d, right? Did I make a mistake? It's x over d. Yes. Plus a constant, plus capital O of 1 over that square root. This is a well-known estimate. This does summation 1 over n is log x plus gamma plus capital 1 over x. Summation 1 over square root of t up to x is 2 square root of x plus constant plus capital 1 over square root of x. Okay, this is analogous to that. So that's what I'm using for the first sum. So what do I end up with? I get 2 square root of x outside. So that's where the 2 square root of x is coming from. And then I end up with summation chi of d over d, d less than or equal to square root of x. Plus c times summation chi of d over square root of d, d less than or equal to square root of x. Plus capital. Now what do I get? The square root of d cancels. I've got square root of x at the bottom. Then I have got summation chi of d, absolute value, d less than or equal to square root of x. I will finish very quickly. Give me 2 more minutes after class. I know my other class is very anxious to get their tests back with their grades, but they wait. All right, so this is 2 square root of x, L1 chi. But the tail after L1 chi is over 1 over x. So that's why it's over 1 over this, so you get over 1. This here is convergent. So there's another capital of 1. That is also a capital of 1. So they're both things capital of 1. This is the first sum. The second sum is this is a convergent series. So you can pull the C out, capital O. 1 over Q is in the order of magnitude of the logarithm. Did I put 1 over Q, 1 over square root of Q? I put the square root. So that's fine. So the second sum is capital O. This comes out as capital of 1. And I have got summation 1 over square root of Q. But Q is only up to square root of x. You will be in trouble if this Q is up to x. Because then this is an order of magnitude square root of x. This is only an order of magnitude going up to square root of x. So this is an order of magnitude x to the 1/4. The last sum is clearly bounded and x to the 1/4. Hence, part 2. But this is bounded, and this is of the order of square root of. Okay. So this is the order of magnitude x to the 1/4. So hence part 2. So this also tells you that since b of x tends to positive infinity, it says that L1 of chi is not just non-zero. L1 of chi is always a positive one. All right. So finally, where is this all leading to? So hopefully, if I write this down, you will say, "Wow, if this is what he's going to prove in January, let me come back to this course." And you'll probably say that after I give back to your homework problems, and you know what your grade is. Okay, so we're going to do the following theorem. Okay, theorem is that the sum of, so this is what we will show. We will prove Dirichlet's theorem by showing the following. So this is a quantitative version. Summation log p over p congruent to L mod k is asymptotic to log x over phi of k plus over 1. See, if I sum log p over all primes, I will get log x. But if I sum this over this subset of primes in the arithmetic progression, I'm going to show that this is the case. I still have this board space to fill. So how do we achieve this? So what is this theorem number? It's 9. So how do we achieve theorem 9? So the answer is theorem 10. I'm going to tell you what theorem 10 is. Theorem 10, and that's your orthogonality relation, is that we're going to write summation log p over p, p less than or equal to x, p congruent to L mod k is 1 over phi of k log x. So that's not the surprising part. The other part is it's a summation 1 over phi of k of the sum over all non-principal characters chi r of h r equal to 2 to phi of k. So you see, there are phi of k principal characters, the phi of k characters mod k, but chi 1 is the principal character. So the other characters I'm denoting by chi 2, chi 3, chi phi of k. So that means it's a sum over non-principal characters, chi r of h, and then inside bar, I have summation chi r of p log p divided by p less than or equal to x. We're going to do this, all right? But now it's not done yet. So why is it I'm going to come back in the spring, or we'll need one more lecture to finish this? This statement is easy. It's consequence of orthogonality. In orthogonality, it tells you that the way to select the residue class L mod k is to multiply by this, and that'll end up selecting the residue class and get 0 otherwise. So if I put 1 over phi of k outside here, I'll get 1 in the residue class and 0 otherwise. That's what is going on. I've divided by 1 over phi of k. Now, forget about this part. If I put r equal to 1, that's precisely the orthogonality relation, chi r of h bar chi r of p, to select the primes in the given residue class. But in that collection of chi r, I siphon out the chi 1. The chi 1 is just 1. And therefore it's 1 over phi of k of the regular log p over p. And that's what is giving me 1 over log x over phi of k. And that's the term corresponding to r equal to 1. Now the terms other than that, the non-principal characters, we're going to show that every one of these sums is bounded over primes. This is over n. From n now we've got to go to primes, even there is good cancellation. So we will show that each of these sums is bounded. That's why it takes one more lecture. Once we show these sums are bounded, this is a sum from r equal to 2 to phi of k of bounded. So this whole thing will be bounded. So you end up with the main term and that. So I'll simply say, we'll show this is bounded. That's where the heart of the whole argument is, where we use the fact that these non-principal characters have lots of cancellation, which is what is. Okay, so now let me return your exams. I'll just tell you one thing. Well, I'm glad that you attempted these problems, and a good number of you got most of the problems correct. Some of you probably work by yourselves. I don't criticize those who get a lower score, because that means they work by themselves. I'm not saying that those who got higher scores sat together around a round table and exchanged answers, but I have no problem encouraging people to have discussions. So that what I'm saying is that therefore I'm not